Hello everybody. I am happy to deliver you a keynote speech today, which will be quite short, but I will give you just a flavor of what my research group is doing. So first of all, about our university. It's one of the biggest universities in Germany, in the city of Muenster, and my research group it makes research on parallel and distributed systems, including distributed systems and clouds, internet-based applications, networking, multi and many core systems, and high-level parallel programming. And we have been involved in many national and international research projects. So if you get interest in one of these topics, then you can talk to me and we can discuss maybe a possible cooperation in the future. Our topic today are real-time online interactive applications, or ROIA. And these applications include, for example, online computer games, interactive e-learning, but also many kinds of training applications and so on. And the main characteristics and also the main challenges of this kind of applications are huge number of concurrent users, very high update rates of the computations, short response times, you see, usually under 1 second, which means that the application reacts almost immediately to user actions, and last but not least, variable load of users, which is dependent on the daytime. So how are these applications developed currently? They sit usually on top of a service infrastructure, and they consist of application processes. And these application processes are programmed using usually C++ or some other high-performance programming language. And the main problem with this development currently is that all these 4 points, application logic, distribution management, network communication, monitoring and controlling, everything is done from scratch for each new application. And you see that we have several application processes. It means that usually these applications, like, for example, modern computer games, online games, they work simultaneously on several machines because one computer is not enough to provide enough performance. And our framework developed in my group, which is called RTF, Real-Time Framework, it liberates the developers from these difficult tasks which are shown here. And how we do it? Now we change this picture a bit, and you see that now the framework is responsible for these 3 issues, and only one issue, application logic, remains the responsibility of the human programmer. The remaining tasks are done by the framework automatically. And now I will show you a short video with an example application, and you see here several robots, and these robots are moving and they are shooting at each other, and if mad they are burning, if shoot they are burning, and then each user is responsible for one robot, and if you have more and more users, then you have more and more robots, and the load on the computers in the network, of course, rises, and the performance of one computer becomes just not sufficient for this load. And you see here that if there are many robots, then their movements are not smooth anymore. And that's why we can automatically add computers using the framework, and also we can then dispose computers if they are not needed anymore. So we have here a seamless experience using our framework. And now we also bring these kinds of applications to the clouds. So you know that clouds have a lot of advantages also for this kind of applications. For example, we can benefit from customized systems, from high scalability, from pay-per-use. It means we pay only for those resources which we really use, and we don't pay for a computer which just stands without being used, which is idle. And the next point of interest for us is a load balancing in such a system. We have several possible load balancing actions, and we have developed this decision diagram which describes how we decide which of these four load balancing actions is really executed. And we decided by checking particular conditions in these nodes, and depending on if this condition is true or false, we go left or right. And in this way, we move in this decision diagram, and ultimately we come either with an acting application or with migrating users and so on. Also, the next interesting topic here are software-defined networks. It's a hot topic today in networking, and we use this new emerging kind of networks for our distributed applications. The idea of software-defined networks is that if you have, for example, here a client, and here you have a server, and they are connected by this network with routers. And then if this connection in the network is overloaded, so it's too slow, it gets congested, then the SDN controller, it's a central entity in the network. It observes this bad situation, and it contacts the routers in the network, and it adapts the network to this situation, such that, for example, instead of this connection, we go this connection, which is probably faster, and so we avoid the congestion in the network. So this is the idea. And so now we can also look at a small demonstration, which is based on the demonstration I showed you already with the game with robots, you remember, which were burning and shooting. And now we have this situation with a client with several servers, and these clients are responsible for the robots. And we have here this connection, and this connection becomes red. It means it's overloaded. Then the SDN controller will see this situation, for example, the situation when the movements are not smooth, and it will reroute the messages instead of this route, instead of this path, along this new green path. And in this way, it will achieve that the movements of the clients, the movements of the avatars in our game will become smooth, and the user, the gamer, will become happy with the quality of service. And we have done a lot of experiments on that, and here you see the results of one of such experiments. What we have here a rising number of clients, so we have the situation that more and more clients are joining the application, and we have the rising CPU load. You see here it reaches 100% by about of 200 clients. It means that the system is very highly loaded, and we have two curves here. We look first on the blue curve, which is the curve of the RT, response time, for so-called normal clients. These are clients who use just the original network without managing it with software-defined controller. And you see here that the more clients we have, the stronger our blue curve is rising, and it means that the response time is rising. And you remember, the response time was to be under 1 second, and here it's of course much higher, and it means that the game becomes unplayable for the gamers, for these normal clients. But if we have premium clients who are ready to pay some money, for example, for managing the network, and we do manage the network using the SDN controller, then we see that in this green curve, we don't have this very steep rise, but it's rising, but only slowly. It means that we have a good response time, we have a good quality of service, and we achieve a better experience for the gamers, for the users of our application. This is the idea of our approach here. So here you see the final slide. Thank you very much. And if you are interested, I will be happy to address and answer your questions. Thank you very much. I'm open for your questions.